Hello everyone, welcome back to this video series on grade 12 physical sciences, specifically paper 2 for National Senior Certificate, DBE. The paper 2, as we all know, is chemistry. In this video we're looking at question 3. Questions 1 and 2, the multiple choice section and the first of the long questions have been done in previous videos. So if you'd like to see those, do see one of the other videos in this series. Okay, so let's dive straight into question 3. So just a couple things I will reiterate. I almost reiterate this every video, but this paper is out of 150 marks. You have 3 hours, which is 180 minutes. That basically means you need to spend roughly 1 minute for 1 mark. Okay, this leaves us with about 30 minutes at the end, which we can use to double check our work and go back to any difficult questions that we may have skipped. Okay, so with that in mind, we can see that our question here is 13 marks. So we don't really want to spend a lot of time on this question. We know that this question is fairly straightforward. We don't want to spend probably not more than 20 minutes trying to do this question. Okay, so let's get straight into it. The melting points and boiling points of 4 straight chain alkanes are shown in the table below. Okay, straight chain alkane, so no branching. It's an alkane, so saturated hydrocarbon. Judging from the names, no functional groups, just carbons and hydrogens in different chain lengths. Okay, so they've given us some data, specifically melting points and boiling points. So let's do some work here. Let's just say how long each chain is. So from the prefix pent, hex, hept, and oct, we know that pent is 5 carbon chain, hex is 6, hept is 7, and oct is 8. Okay, like octopus. 8 legs. All right. So let's get into the first question. To find the term melting point. So with definitions, I always say that you can say it in your own words. You can try to memorize definitions in a way that makes sense to you. Whatever's easiest. Sometimes memorizing the textbook definitions are not the easiest. But however, whichever way you decide to do it, whichever way you decide to phrase your answer, there have to be some key phrases in order for you to get full marks. So I'll give an example answer. This will be the temperature which solid and liquid phases are in equilibrium. Now that's a very textbook definition, but unfortunately it is the answer that required. It is the answer required. So technically saying something like the temperature at which a solid starts turning into a liquid, yeah, you might get 1 out of 2 marks for something like that. Or yeah, so the key words in this answer to get the full marks is you need to talk about temperature. Okay, melting point is a temperature. And yeah, of course it's the change from solid to liquid, so you have to mention the 2 phases. And then for the final mark, it is a bit of a technical definition, but you have to say where they're at equilibrium. That's really tricky, but that's the answer we're looking for. Okay. All right, so it does some of these definitions You can phrase them in your own way, whatever way makes sense to you, but they just have to have the key phrases in order for you to get the marks. Okay, question 3.2. Write down the general conclusion that can be made about the melting points of straight chain alkanes. Okay, so let's come back to our data here and let's see what we can see. Okay, so for now we're just considering melting points. Okay, so melting points. Okay, we're not gonna worry about boiling point for now. And what we can see is that the melting point increases from pentane to hexane, and the melting point increases again, okay, from hexane to heptane, and finally the melting point increases again from heptane to octane. So a fairly reasonable conclusion would be the longer the chain, the higher the melting point. I'll just say MP for melting point. Okay. Yeah. So that's a fairly reasonable conclusion. The answer being looked for here can be phrased in a couple of different ways. So let me just give you some alternative answers. As the chain length or number of carbons, carbon atoms or molecules, or you can talk about mass or surface area. You can also talk about strength of intermolecular forces. As all these things increase, the melting point increases. So yeah. So we've just said the longer the chain. So this does imply like this is sufficient to answer, but instead of saying longer chain, you could say the number of carbons, you could say the molecular mass, because technically these increase in molecular mass. You could say surface area as well. Surface area is actually the true reason why, because the longer molecules have a higher surface area, which means they have more contact points for stronger intermolecular forces, or they have a higher cumulative effect from intermolecular forces. So that is the real reason why we see the increase in melting points. So a couple different ways to say it. You could also say the reverse. So you could say as the chain length increases, as the chain length decreases, the melting points decrease. So you could have chosen to look at it this way. It's the same thing. You're saying the same thing, just in the other direction. And that's acceptable as well. So yeah. Most important thing is you just need to see the concept of the independent variable and the dependent variable. So here, what are we controlling? So we control the independent variable, and that is the chain length of our compounds. We choose what compounds to analyze. And something out of our control is the melting point of said compound. So as we change our independent variable, the chain length, the dependent variable, the melting point changes, and you just have to see that trend. So yeah. No need to overcomplicate the questions, only for 2 marks. So yeah, in a real test, I mean, this is good for 2 marks. You don't have to think too hard about this, and then you just keep moving. Okay, name the type of van der Waals forces between molecules of octane. Okay, so this you should just know by head, but just to remind ourselves, we'll draw octane. Okay, so this is octane. There's 8 of these, and then there's hydrogens here. Okay, to save time, I'll just draw the hydrogens as sticks. I won't write the H's. Now the thing is, carbon bonds, not very polar. Carbon hydrogen bonds, again, not very polar. There's very little dipole forces in these molecules. There's very little polarity. So what you realize is, yeah, anything like hydrogen bonding is out. Okay, hydrogen bonding is out. Dipoles are out. There's no polarity in these bonds. So it's technically the weakest van der Waals force that we can have in this molecule. And these are London dispersive forces. Okay. And they're just, I guess all these types of bonds are all the same. They're all based on dipole moments, but it's just they have different names because they have different strengths. So London dispersive forces. Okay. So for this test, you don't have to say dispersive. You can just say London forces, but strictly speaking, it's London dispersive forces. Okay. So again, just something you have to know. In a saturated alkane, you're only going to get London forces, nothing else. Okay. Write down the predominant phase of the following alkanes at a negative 100 degrees Celsius from gas, liquid, solid. Okay. So basically, we're going to use the data they've given us to decide if at a negative 100, what phase pentane and octane would be in. Okay. So pentane at negative 100 is definitely solid because it only melts. Oh no, it's definitely liquid, sorry. It melts at negative 30. Yeah, so negative 30, it already melts, and then at 36.1 it boils. So yeah, so here it becomes a gas, here it's solid, and here it's liquid. Okay, so this is alpha liquid. Okay, so we can do something similar for octane. So octane at, so we have negative 100 way down here. Then they tell us its melting point is at negative 57 and its boiling point is at 125. Okay, so after this we have a gas, here we have a liquid, and here we have a solid. Yeah, so over here S for solid. Okay, very straightforward, I'd say. Let me just clean this up a bit so that we can see the next question. Okay, hexane is now compared to 2,2-dimethylbutane. Is the molecular mass of hexane greater than, less than, or equal to that of 2,2-dimethylbutane? Okay. I guess, I mean, there's a trick to answer this question very quickly. But I guess let's just draw it out to see. So I'll draw the stick version. So hexane is 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. Sorry, hexane has got 6. Hexane has only got 6. Okay. Then 2,2-dimethylbutane. So let's draw butane. So butane has 1, 2, 3, 4, 2, 2. So okay. Now we can just quickly count. So here we have 6 carbons, and then we know from our homologous series that anything like this would have 2n plus 2 hydrogens, and n is 6, so 14 hydrogens. Okay, here we have 6 carbons as well, but the hydrogens, unfortunately, we have to count them. So there's 3 in the beginning. Okay, let me use my highlighter. So we have 3, 3, 3, 3. So that's 12. There's none here, and there's 2 here, so that's 14 as well. Okay. So actually, yeah, they have the same molecular mass. Okay. So equal. I don't know why I wrote a capital Q. Let me rewrite this properly. Yeah, okay. Equal. Give a reason for your answer. What? What do they want us to do? Okay, I mean, I guess just explain. So you could just say they have the same molecular formula. You could say they're isomers of each other, chain isomers. That's acceptable. So you say isomers. Is the boiling point of 2,2-dimethylbutane higher than, lower than, or equal to that of hexane? Lower, yeah. You see, the thing is, this branching here means that when the molecules pack, okay, so the packing of the molecules, this space is greater compared to when we have hexane. Yeah, this space is very small. So these molecules can't be as close to each other compared to hexane, and that means the intermolecular forces are weaker. Yeah, so IMF are weaker. So because IMF is weaker, that means we need less energy to boil 2,2-dimethylbutane, so it'll definitely be lower. And yeah, we've already explained here, as I've shown here. But we can give a more formal definition maybe, since this question is like 3 marks. Okay, so firstly, they want us to compare the structures. They want us to talk about intermolecular forces, and then they want us to talk about how the forces relate to energy and how that relates to temperature. So what we could say is 2,2-dimethylbutane has a more branched structure, so smaller surface area over which intermolecular forces act. Therefore, the intermolecular forces are weaker, and you can name the forces van der Waals or London forces. Therefore, lesser energy is needed to overcome the intermolecular forces. Yeah, and that gives you the marks. So the thing is, you can talk about it from the perspective of dimethylbutane or from hexane. So the other way to say it would be hexane has a longer chain length, so there's a larger surface area over which IMF act over. Therefore, IMF are stronger, and therefore more energy is needed to break the IMF or intermolecular forces. And that's good for 3 marks. Yeah, and that's question 3. Great.